hook a sight glass on here, and I'm going to follow this sight glass, and I'm going to replace this sight glass reading by time. So we've never really addressed time. And the great advantage of not addressing time is this. I've never had to tell you, this is what you want to observe. I've never had to tell you, I've never told you anything about V, whether it's constant, whether it's variable. It has never mattered because I've scaled this problem with respect to L instead of with respect to T. Okay, that's the first thing to observe. I've never had to tell you anything about V. I've gotten rid of it. Now, I've been telling you that if there's an L in here, I read my sight glass and get L, but you know that's not true. When you read the sight glass, you get volume. However, your balance equations, your equations, are in terms of L. So, what the heck's going on? I would like to know what volumes mean in terms of L. So, let me make an assumption. Here's an assumption. The assumption I might make to begin is that this is an ideal solution. So I might say the volume is equal to L times x1 v1 bar plus x2 v2 bar. So these are specific volumes of the pures, and that's what I can get away with putting pure component variables here or values here because I've assumed an ideal solution. Now, what does this tell me? Even if I assume these V's are constant, even if I assume V1 bar and V2 bar are some constants, I still see that volume depends on, and how shall I write this? So for this, I would say something like this. I would say the volume in there divided by the volume in there times 0 is equal to L over L0 times x times V1 bar plus 1 minus x times V2 bar. What does this tell me? This tells me that if I'm reading this, I'm not getting this. What I'm getting depends upon the composition at the time. But I happen to know how L and X go together, but you can see they go together by our integral formula, wherever it was. So you can see that if somebody says the following, boil off half the volume, you're going to have trouble deciding where to stop in L. So you've got a very interesting problem to go try and work. So that's one addition over and above the plain vanilla problem. So you can see that it's possible to make these problems hard. Now, there's another variation that's sort of interesting. It's also a practical one. I might have something like phenol and water. It might be dilute. I might be willing to write y equals mx for n being the slope of the equilibrium curve at x equal to 0. However, the boss comes and says, look, you've been heating this with this heat exchanger. every so often we've got to go in there and we've got to clean up the tubes because the heat transfer coefficients become too small. I'm tired of doing this, so I'm going to get rid of that heat exchanger, and I'll do this. I will take this stuff here and I will heat it with steam. So I'll just put steam in there at some rate. That will create the vapor I need. And I'll go look at my problem and try to answer all the same questions. So I say, okay, so this is steam. And in the dilute case, this is more or less steam. So I do this. I go back to square one, I write my balance equations, so that's really the message here. You always go back to square one and write your balance equations. So what do they look like? They look like this. dxL dt equals minus y of v, no change. However, dL dt is equal to S minus V. So I say to myself, this is a kind of a funny problem, but these are both steam. So I will say the biggest change I'm going to get when I do this, I can get by simply assuming reasonably S equals V, therefore dL dt equals 0. So that's new. I can't go deal with these equations as I did before. So what am I going to do? Constant L, so L is equal to L0. So I go to this equation up here and I say this is L0 dx dt equals minus y v. So I will take the dt over to this side and I will write dx equals minus, and I'm doing dilute, so I can make this assumption without any trouble. Y equals mx. So I have minus mx, mx there, that's for y, there's the minus. Here is the v dt, and there's got to be an L0 in here somewhere. So there it is. Now, I'm no longer tracking time with the amount in the pot. The amount in the pot's constant. Time's moving on. So I've got to do this a different way. So the thing to do is simply observe that dx over x. So I have d log x equals minus m over L0, integral from 0 to t of v dt. But the integral from 0 to t of v dt is the amount in the pot, t. So I learned that my x is varying as the amount in the overhead product tank varies. So I'm going to track time essentially with the amount in the overhead product tank. So here's what I have. I have log x over x0 equals minus m t over L0. So I write x over x0 is e to the minus m t over L0. So as the amount in the overhead increases, I can calculate the x in terms of the x0 and the L0 and the slope of the equilibrium curve. Now, here's the thing. I might want to know what y-average is as I'm moving along. So I say, yeah, I know how to calculate y-average. It goes like this. So let's calculate the average composition as the tank fills. Y-average T equals the integral from 0 to T of how do I want to do this? I want to write in here what that is. Well, it's y dt. No, it's not y dt. It's y v dt. Okay. I guess I can deal with that. Y is mx. So it's m, the integral from 0 to t, of x v dt. So it's equal to m times the integral from 0 to t of x dt. So to get y-average when the tank has that much in it, I got to do the integral from 0 to t of x dt, multiply it by m, but I have that over here, I think. Yeah, x is x0 e to the whatever. So this is going to be mx0. The integral from 0 to t of e to the minus, whatever it says over there, mt over L0 dt. So I can do that integration. I am now going to be able to track the average composition in the overhead as the tank fills. So it's equal to ML0, no, it's MX0. I'm going to have down here an M over L0. I'm probably going to have a minus sign. I'll remember that. So I'll get rid of that minus sign like this. Clean, y-average. So here's how my y-average is going versus t. You give me a t, I can calculate y-average. You give me a y-average you want, I can calculate the t at which you want to stop. All right? So you can see a person who's even slightly awake can make up all kinds of problems based on this. So then the question comes up, can we do anything at all if C is not 2? Turns out if you're willing to make an approximation of 2 or more, you can do something with that case. Let's suppose C is 3. Now, one of the things that happens to you when C is 3 is, I can't draw so many pictures anymore. So I'll start with my balance equations. And I'll see what I have to do to get something good. My balance equations must be d of xil divided by L equals a yi. That's for all I equals 1 to C or 3, 1, 2, and 3. So I get these 3 equations to solve. So here's what we'll do. We'll take this equation for I and we'll divide it by the equation for j. So I will have d xil dxjl equals yi divided by yj, which is equal to alpha ij xi over xj, which is equal to alpha ij xil over xjl. No approximation. that equation. Here's dxil. There you see xil. Here's dxjl. There you see xjl. All I gotta do is say something about the alpha ij's. Well, the only reasonable thing to say is, suppose the alpha ij's are constants. Not really constants. They might be close to constants, or they might not. So if they're not, we're not doing that problem. If they're not close to constants, we got to go and do the problem as we set it up last time, which is horrible, but we don't want to do that. We can't get a formula that way. We can just get tables of numbers. And there's not a whole lot you can do with tables of numbers. So I'm going to assume the alphas are constants. So what have I got? That gives me dxil over xil equals alpha ij dxjl over xjl. So I integrate it. And here's what I learned. I learned that all these I learned that xil over xil at time 0 with a log equals alpha ij log of xjl over xjl at 0. So now, this is true for all I and j. So I got a bunch of alphas. I got alpha 1, 2, I got alpha 2, 3, I got alpha 3, 1. They're not independent, of course. So, how am I going to make use of this information? I'm going to make use of this information in the following way. I have a condition that's going to help me deal with this problem. The condition is simply this, that x1 plus x2 plus x3 equals 1. So I'll multiply this by x1, 0 divided by x1, 0. I'll multiply this one by x2, 0 divided by x2, 0. I'll multiply this one by x3, 0 divided by x3, 0. That'll be 1 still. I'll multiply this both sides by L over L0. So I have x1, 0, L, I guess I should just write this x1L over x1L0 plus x2, 0, x2L over x2L0 plus x3, 0 times x3L over x3L0 equals L over L0. Okay? Now, pick one of your species. Maybe you'll pick X3. So you'll say something like, how have I written these stupid things down there? I've written this way. I pick X3, and I'll write every one with respect to X3. This will give me X1. Okay, that's probably a good move. So I will say something like this. X1L over X1L0 equals X3L over X3L0 to the alpha 1, 3. And I'll write X2L over X2L0 equals X